Hello, once more. Welcome back to the desk. First up, apologies for last week. Things got in the way, so I didn't really have the time, unfortunately, to do the video. So this is the video I was going to do last week. So, when you're using a microcontroller, such as the ESP32 here, sometimes you need to do more things than you've got pins for. This has a number of pins. You can't use them all. Some are power pins, some are going to be used for other things. What if you need more pins? What do? Well, what you need is something called a port expander. Now, this is a clever little blighter. There's an example here we shall look at in a minute. This can take a few wires to control multiple things. So what you can do is you could say, this is next to it. You could say, right, I want to control these 4 LEDs and I want to read these 4 switches. Warning, contrived example. So that is obviously 8 wires. Now you could run 8 wires to this. What if this is a bit further away? What if this is on a control panel? And this thing is under your board somewhere doing other things. You really want to run a bundle of 8 wires? Yeah, maybe not. Now there are many of these devices. The one we're going to look at today is called a PCF8574. It has a slightly bigger brother called a PCF8575, which I'll sort of mention towards the end. There are also 74165 and 74595 devices we're going to look at in other videos. There's an MCP23017, which I've got somewhere. In fact, I've actually got 2 of them somewhere. No idea. You can also use another microcontroller as a port expander. For example, this could talk to an Arduino over a serial link and access all the pins on the Arduino, could do all the reading and then send data backwards and forwards. So what these devices do is they provide a way to connect a number of digital devices. Note digital. There are ways of connecting analog inputs as well, but this is just digital. To a communication bus of some sort. This, for example, uses the I2C bus we used in the displays video to drive the liquid crystal screen. Funnily enough, actually using a chip that's a slightly different version of it, but a PCF8574 to do it. This was the black surface mount chip on the back of the little backpack board. Some of these devices only provide output. The 74595 is an output-only device. Some, such as the 74165, are only input devices. This little blighter is quite clever because it can do both. So without further ado, let's move on with this. We're going to have a little look at the PCF8574, how it works, what it can do, how to use it, and then what you can use it for, perhaps why you should have a look at it. Let's get on with this. Okay, start off. What is a PCF8574? Well, the datasheet, always my good friend here. So here we have a datasheet. This is for the NXP version of the 8574. There are different versions of this. And here is a pack. It originally had 6 in it, and one of them's here. So the datasheet describes this as an 8-bit input-output I/O for short, expander for the 2-line bidirectional bus, which is the I2C bus. And it also notes it's designed for 2.5 volt to 6 volt operation. That's quite nice. In practice, what you've got, we'll look at the one here. This is a 16-pin dual inline package, DIP. Really good because it fits on breadboard. They come in other formats. I'm just trying to see if I can find some pictures of some of the other formats these things come in. The back of the datasheet's normally a good place to look for this sort of thing. And yeah, it's in here somewhere, but anyway. The other ones you can have on this, there are SO16s, which are surface mount, and SOP20, which has got more pins on it and is a square format. There's lots of different ways. For model railway, these ones are the good ones to use. You can get these on breakout boards with little jumpers to do things and pin terminals and what have you. So what we need to do is have a little look, and I'm just going to flick into the in here. into this NXP Semiconductors datasheet, and I'll move that out of the way because foreshadowing with the switches and the pins. This is, as it says, a block diagram of what we've got. So there's an I/O port, which is basically a registry. This connects directly to the pins. There's a shift register, so you can write information into this, and it communicates. Interrupt logic we'll have a little look at later. There's the bus bit, which is how it talks to what it's doing with various bits of filtering. There's a reset, and it goes around. So what we can see here is there are 3 lines to the processor, really, which is that one, and that one. This is how it communicates with the microcontroller. Processor is basically the I to C bus master. Interesting, it's not just microcontrollers. You can connect these things to like Raspberry Pis, which has advantages because if something goes wrong, you'll blow up this. These are cheap, instead of blowing up a Raspberry Pi, which can be quite a bit more expensive. We also have the power lines. So we have a supply line and a return, VDD and VSS. And then we've got these 3 curious little beasties, A0, A1 and A2. Well, if you remember, and we'll look at this in a little bit more detail when we come to actually wiring one of these things up, the I to C bus uses a device address. Well, you can use these pins to set the address. Now what this means is you've got a 3-bit number. This gives you 8 possible addresses this thing can have. So while this has got 8 outputs, you can actually have 8 of these on your data bus as well. So just using these chips, if you use 8 of them, you can have basically 2 wires. We'll come back to the interrupt wire. And control 64 inputs or outputs with just 2 wires, which is, yeah, it's quite impressive. And I say that this thing's got another trick up its sleeve, is you can read and write information on these. As I said, some chips do one or the other. Here it's configurable. It's configurable in quite an interesting way. There are other chips, and they have like a data direction register. So you switch it on, you then tell it which pins are going to be inputs, which pins are going to be outputs. And then sometimes there's different commands for reading and writing things. This little beastie you don't have to tell in that way. You can actually change it dynamically as well as you're going. So you could have, P0 could be an input sometimes, but sometimes it might be an output. I've never come across a need to do that, but you can. There's a technique called multiplexing you can use on these things. So, well, how do we actually use this thing? So let's put the datasheet to one side. We'll come back to that because it's got some quite interesting information in it, which we will use. So here is the chip. So the first things we need to do is we need to connect power and ground. Now, I've already done that. This is power, goes to this pin up here, ground goes to this pin down here. And if I just have a little look and say how, I will refer back to the datasheet straight away. This is the pin out of it, so I've got it sort of that way round. So VDD, if you look down here, it says it is your supply voltage. And VSS is the supply ground. So that's what we have. Supply voltage, supply ground. This is going to run on 3.3 volts. As we said, this works at anything between 2 and I think about 2.5 volts and 6. So that's connected. Now the next thing I'm going to do is connect the address lines, and I'm just going to angle this slightly because it'll make it a little bit easier to get these wires in. You'll pardon my excuse my fingers in the way. Yeah, cut these earlier just to try and get them to fit properly. Right. So I'm going to connect these all to ground, and what this does is that says these 3 pins are going to be 0. And in hexadecimal, this thing's address is 20. Get in there. 20. I'm not even sure that's gone in. 20 plus whatever are on these pins. And you do need to set these pins. If you don't set them, ask me how I know this causes problems. If you don't set them, they get floating values and they can pick up interference. I'm just going to try and sort that one in the middle out a little bit. Yeah, they can pick up interference, and you sometimes find that the chip doesn't respond when you think it should, and other times it will, and then for a little while it won't, and then it will again. Because of these pins floating, it's changing the address it talks to. If you connect them to 0, it talks to 20. If I connected the A0 pin to ground, positive, this would now connect to address 21. It's like, and this is useful. Leopard Street, I use this thing's slightly bigger brother, the 8575. Two differences and why I'm not using it for this example. Firstly, it's surface mount only, so it comes on a little breakout board. And I don't have one to hand. They're all on the layout downstairs. But that's got 16. It's basically the same chip, but it's got 16 input outputs. So, 8 on one side, 8 on the other, and away you go. Same addressing system. What we now need to do is connect up the data lines here. Now, we have... I'm just going to have to work out which ones of these go to where. So, that one is going to go to that pin. And the other one goes over here. So if I do the short one first. The shorter one is this pin here. Now, this goes in like so. And these are the I2C data lines. Now, I was going to try and be terribly clever when I did this. I was going to actually be using an ESP8266. It's a lot smaller. It has a lot fewer pins. Really showing the benefit of these things. I couldn't find one. I've got several around somewhere, but I couldn't find them. So they're the I2C data pins. The next one along is an interrupt pin. We're not going to connect that now. What we're going to do next, though, is leave it at that. And we're going to connect it. And we're going to see what it does. Because what it does, when you don't configure it, I say it's interesting. For a given value of interesting, shall we say. I'll just put that way, plug that in. So that's now switched on. So if I just do this, we can jump back over here. I'm going to minimize that bit a little. So what we're going to do is set this up. So the first thing we need to do, as always, well, nearly as always, we're going to use a library. And this is the library we're going to use. PCF8574. If you go into the library manager, PCF8574, and the one I use is this by a guy called Rob Tillart. It's a really simple library. You can read and write individual pins, or you can do what I do, which is just read and write the lot in one go. So we've got that. The first thing, because we want to see what this is doing, as we've done in previous examples, I'm going to put the serial port in. I'm also going to put something in so that it writes out, basically so I know what it's doing. What we then need to do is these two little lines here. Now the top one does matter. If you don't do that, it won't work. Some libraries that use the I2C connection don't need that. This one does. Basically, some have it in their internal code and some don't. It's just a line you need. And the one below here says PCF begin. So what we need to do is define our little object. So I'm going to come back up here. I'm going to do that. So as we've had before, we're going to create an object. I'm just calling it PCF here. That's the address it's on. And now we work. So what we're now going to do is I'm going to come down into here. And I'm going to say, I'm going to create a variable, 8-bit variable. I'm going to call it val for value. PCF read 8. There we are. And what that's going to do, as this says, is read all the pins. I think, well, I've not connected them to anything. I mean, they're literally not connected to anything. So what's that going to do? Yeah, we'll see. We'll see. I'm then going to copy in a little bit of helper code. Now, this, don't worry too much about what this is doing. this is going to take this 8-bit value and it is going to show it as a group of 4 ones and zeros and then another group of 4 ones and zeros. It's just something I'm using here to help make this perhaps a little bit clearer. So we've read the value. I am going to run my little print routine here, which will stick it onto the output. And what I'm then going to do is delay for 1000. Let's see what it does. I do hope this works. We'll see. It worked earlier. Here's how it goes. Goes to its little loop routines. Here we go. Connecting, and it's uploading nicely. Which is good. So we jump over to here, clear that, and if I do that, it'll reset. And it's showing all ones. Why does it do that when it's not connected to anything? Well, again, we have a little look at the datasheet, and it says on here somewhere, I'm just trying to find where. Here we are. So, internal power on reset initializes all IOs as input with a weak internal pull-up 100 microamp current source. That's nice, isn't it? What on earth does that mean? Well, what it means, each one of these pins, when it's an input, it's connected internally to a power supply. And this is how they switch on. Some chips are pretty good at inputs and outputs. This one isn't. So what we're going to look at here is exactly how these things work. Or at least in principle how these things work. Because you need to put a little bit of thought on this. So I'm just going to shift that slightly and go here with a piece of paper. So we have a pin. Now on a microcontroller, that could be an input, could be an output. Say we're using an Arduino, you can put, you can take out of that 40 milliamps, and you could put into it 40 milliamps. Don't go much above 20. 20 is your sort of limits. Well, the way this works, this can take in 20 milliamps. In fact, it'll take in 25. But it can only put out a very small amount in the microamp range. And this is because internally, each of these pins, there is a little diagram for it, but it's not terribly clear what it's actually doing. But basically, when it comes onto an input, it puts this low current source on there, and then if it, you can try and drive something with that if you want, as long as you don't mind it being, in the microamp range. But you can also say, well, I'm just going to pull it down to 0. Then it will see it. So if I bring this back here, move my bit of paper out of the way and see if I can find a suitable piece of wire from the mess I have lurking here. Here we are. What I'm going to do is take one of these and I'm going to do this to it. And if you look at the top, you can see that 1 has become a 0. And if I do that, different one. Go up here. Different one. So if I connect any of these down to ground, it detects it, which is quite nice. This is incidentally how I'm using this on the layout. I have some sensors that normally sit and go, yep, positive voltage, quite happy with that, and it says, I've seen something. I'll drag it down to ground. So it is an active low sensor. These chips work brilliantly with active low devices. What if it's an active high device? Well, it would normally be sat sort of, usually active high means it's it's not doing anything normally, and they'll connect to high. Can't tell the difference. So if it actually outputs 0, this will pick it up. But normally, yeah, inputs like that. So what I'm actually going to do is I've got these little switches up at the top, and these are set up to connect to ground. So I'm going to put some bits of wire in here, because if I do this, it's a lot easier than messing around with those bigger pieces of wire. Not that one, that one. And then you can see what I'm doing. Incidentally, I'm using these little pre-cut well, I say pre-cut, I've pre-cut them, jumpers. This sort of wire is perfectly valid when you're playing. I'm just not using it here because it makes seeing what I'm doing a little bit harder. So I found if I pre-cut some of these, away we go. So these are all in here like this. And again, note over here, all zeros. Well, switch that one on. Yeah, picking up a 1. Switch that one up. It's picking up a 1. That works. That's input. So basically, connect it to ground. You don't need pull-up resistors. You just literally connect it to ground. It'll see it. Or you don't connect it to anything. That works quite nicely. These could be push buttons. I mean, I've used one of these things because it fits and it's easy to work with. So there we go. Now, this is pulling that pin to ground. So this is taking that tiny little output current, dragging it down to ground. The pin inside that can see this, the ground is much stronger. That tiny little bit of current can't overcome that. But it flowing to ground doesn't mean anything. It's tiny. We can forget about it. So this, I believe it kicks out on the, according to the datasheet, this is 300 microamps. So when I do that, I've got 300 microamps going through there. You can sort of light an LED from that, but it's stupidly low levels of current, and most LEDs won't work with it, so I'm not going to try that. So how do we light the LEDs? Well, what we do is we do it the other way round. So normally you would take the pin, say from your Arduino, you would bring it out, you would go through a resistor, and then you would go to ground. And if you put logic high on that pin, the LED will come on. Now if we go back a few videos, I had one pin driving 2 LEDs with one on or one off. We can use the same sort of technique here. We can sync current. That means current goes into this and then out through to ground. So what I've got is these LEDs. These all connect to the positive voltage. They then come through here, through 1K resistors. Just a note, always use a resistor. Even if you don't think you need one because you're using a little battery or something, use a resistor. So yeah. You want to be in control of the current. So what I'm now going to do is I'm going to connect these to the other 4 pins. And we'll see what we can do. Now, to start with, all of these pins are at a logic level of 1. So they are at high. In this case, that's 3.3 volts. With very little current capacity. So I've got 3.3 volts coming down to 3.3 volts. There's no current flow. The lights are off. But it says over here, it says 1. So 1 means off and 0 means on. It's something you need to play around with on this. Anyway, that's most of the wiring. There is another wire. There's a little orange wire up here lurking. We'll come to that one in a minute. So, how can we read this and write it at the same time? Well, if we come back to the code, it's actually quite simple. What we're going to do is to start with, we are going to have we're going to write this value back out, but we're going to modify it slightly. So what I'm going to do is val equals val ding ding 4. Okay, right. What on earth does that do? Well, if I start with a value that looks like that, I'm just going to put this in comments, otherwise at some point it's going to break. If I start with that and say I'm going to do a 4-place bit shift, which is what this thing does, to the right. What I'm saying is I want to take each of these bits and move them to the right. Well, can't go beyond that, so that first we'll do the first bit shift. That naught, well, it disappears. And another naught will appear at this side. And if we do that 4 times, what we'll end up with is 2, 3, 4. And here, what that's done is say, take these high 4 bits. These are the switches, because this is pins 4, 5, 6, and 7. The 1, 2, 3, 4 down here. Incidentally, this is why these wires cross over effectively. It's 1, 2, 3, 4, 5, 6, 7. Not 1, 2, 3, 4, 5, 6, 7. Yeah, across there. So we need to shift it 4, and that says basically take what's on the switches and put it on the LEDs. Straight, not doing anything else. However, if we write that back out, what we've now just said is I want these switches up here, I want them to be outputs. This is where it gets a little bit curious. You can only write a 0 or a 1. Now if you write a 0, you're saying I want this pin to be an output and I want it to be at a low logic level so that it can sync current coming in. You can also say I want this pin to be a 1, and that can have 3 different meanings. The first one is that could be I want this pin to be an output, but I want it to be at logic level 1 so that it won't sync current. It'll source the 300 milliamp. In this case, that would mean the LED's off. You can also say I want to write a 1 to this because I want it to be an input, and then it can be a 0 or a 1 as the inputs. Yeah, a little bit weird, but it works. So what we're now going to do is we need to modify this because I need to say I want those high bits to be, they have to be a 1. So what we're going to do is this one. 0B 1, 2, 3, 4, 1, 2, 3, 4. Now that is a logical OR operator. It's basically saying I want this value to be itself ORed with that. And what that'll do is say I don't care what these top 4 bits are currently. They're now a 1. And the lower 4 bits will say I don't care what those lower 4 bits are. Leave them alone. So we've shifted that and we've got that. And what we're then going to do is we're going to come in here and go PCF.write 8 val. And again, we'll stick with this little delay down at the bottom. This little code messes up in a minute, but it works for now. So let's just run that and see what it does. Now, it's worth noting, this is an 8-bit operation to bring this in, bring this out. If you've got 8 of them, you're going to have to read all 8 individually and then write all 8 out individually. But once you've done that, you're away. So that's reset. Clear that. Still going. But if I do that, it might be a little bit hard to see, actually. Let me just turn this light off. There we are. Yellow LED is on. Yeah, shade that. There's a window that way. If I do that one, they come on. If I turn them all on, all of the lights come on. Now, because I've put this code delay in, there's a little pause between me flicking a switch and it doing something. But this is now reading these switches and putting it onto here. And the only wires we're using really between the chip are these two. Everything else has been done by this little beastie here. So you've got to be aware that the logic is backwards in many ways here. A 1 is a 0 and a 0 is a 1. Yes. Anyway, it's once you get your head around it, it works. It basically is you have to wire the LEDs the other way round so that the current flows into this chip instead of flowing out of it. And then if you write a 0, the LED will come on like that. And this you can drive anything you want that's digital on this. Anything that wants a 1 or a 0. But again, you want something that effectively becomes active low. So these aren't always suitable. If you're using something that drives off a transistor, for example, you would be using a PNP transistor to feed current into this instead of an NPN where you're feeding current out. And that particular piece of witchcraft we will look at in more detail in another video. But this little delay, this is called polling. So we're saying to this every second, because this is the only little loop we're doing up here is this bit. We're saying every second, read this, do something with it, and write the result out. And depending on what you're doing, that might actually be enough. But usually what you find is when something changes, you want to know about it immediately. Well, there's a fairly simple way of doing that. However, what I'm going to do is disable that before I do it. Otherwise, the thing below goes a bit bananas. All right, let's change polling frequency. Instead of doing it once a second, let's do it 10 times a second. And it should get a little bit better. Here we go, let this compile, let it run. Here we go. I mean, as you can see also, you're not using very much code to control this thing, which is quite nice. And there's not lots of bits setting it up. So anyway, here we go. That now runs a lot faster. And in many ways, that sort of, I mean, you have to play around with it. It worked. I just like making LEDs come on and off. Now, with some of the other chips, if you use a 74165 input, firstly, it's only inputs, so you'd have to have one of those and a 595 output, but you could have 8 switches and 8 LEDs. And when I come to look at those chips, that's what we'll do. You've got to read it constantly, which is what we're doing here. This is this polling. But if you're doing a lot of other things, you might not want to wait for this. I mean, say if you're reading a lot of these things, it's not a particularly long operation. This data bus runs at 100 kilohertz. So it's shifting a fair bit of data, especially when you're only talking 8-bit values. But this polling is messy. But if you're using certain chips, you don't have a choice. Here you do. That's what this interrupt line's for. So what I'm going to do, I'm going to find the orange wire and I'm going to connect it. And then we're going to make it work and we're going to see what it does. So that goes into there. I'm connecting that to pin 19. There are options. If you're using an Arduino, pins 3 and pins 2, they're the only ones that take these interrupts. Sorry, an Arduino Uno or an Arduino Nano. The Arduino Mega has got more pins it works on. The Arduino Leonardo has got 6, but they're on. It varies a little bit. But I don't want to do this polling. Don't like that. So I'm going to get rid of it. I want to read this when something has changed. And this is one thing this little chip excels at. This will monitor its inputs. It monitors all the pins at this time. And if anything changes, it'll tell you. So how do we do that? And we have to come back up to the top. Excuse me there. We need to define 2 more things. Up here. Firstly, we need this little flag. And this is where we're going to say something has changed. So to start with, false. Nothing's changed to start with. This keyword here, volatile, matters. Normally when your code is running, it'll say, oh, I need to reference this flag value. Excuse me. So it'll go in and do it. And 2 or 3 lines later, it'll say, oh, I need to access this flag value again. It won't go and get it again because it's sort of got it within the chip already. This volatile bit says, go and get it again. Don't be lazy, go and do it. Takes a little bit longer, Not that you're going to notice the speed computers run at, but if you don't need it, you don't use it. It just basically says this value is volatile. It may have changed since you last looked at it, because we're going to be using an interrupt which is going to change that, and the compiler doesn't know when that interrupt is going to run. And then here, int pin 19, so the interrupt is on pin 19. Just drag that over there and line these up a little bit better. It just looks a bit neater. There we are. Slightly OCD in code, but it helps. We now need to come into this area here, and firstly I need to tell the system I want that pin to be an input, and I want it to put a pull-up resistor on it, because this is an active low chip on the interrupt line. So what it does, this line will sit at 3.3 volts, and when this chip says I've got something to say, it will connect that to ground. And this, you want your microcontroller to notice that. Now you can poll that pin. You don't have to use an interrupt. So if you've got a lot of these things, you could say, well, actually, I want to look at them separately. So I want to know which one's gone. But because of the way this works, you could actually have, well, potentially 8 of these things all connected to the same pin. And if any of them notice something, they'll drag it down. And if 2 of them see a change at the same time, they'll both drag it down. Doesn't matter. You obviously then don't know which is which, and you've got to read all of them, but that's fine. So we can define the interrupt as such, and here we go. And what this says is that pin and this digital pin to interrupt bit just sets it up so it works properly. This is the pin. This says this is the pin I want to look at. Falling is I want to look at this pin when it goes from a positive voltage, like 3.3 volts, down to 0. Don't want to trigger the interrupt again when it goes the other way. You can get it trigger on both. And this PCF_IRQ, this is the function I want it to run. Now, we haven't defined that yet, so I'm going to add that. I'm going to put it up here. And that's all it does. Now, something that's to be aware of, when you're running these interrupt functions, you want them to be as quick as possible. You want in and out as quickly as possible, because it could call it anywhere. I mean, we could be there, say, we're printing this out, we get to this point, the interrupt calls. So it'll run, and then we'll come back to here, and away we'll go. For similar reasons, do not put serial statements in here. It's very, very tempting. It's tempting to do, I'll do code, I'll do calculations, I'll do all sorts of stuff in an interrupt. Don't. You can do some very quick calculations, like incrementing a counter or something. Do it this way. Set up a little flag so that when this triggers, it will set that flag. Now we're going to come down here, and I'm going to modify this slightly. So I'm going to go if flag. So if that interrupt flag has been set, we want to do something. And the very last thing I want to do on the interrupt, this is false. So we're going to do something, and I'm going to set it to false so we don't do it again. And what we're going to do is this. So I'm just going to copy that. I'm going to put it in here, and I'm then going to mess around with the formatting again so that it looks a bit better. So what we're now saying here is, if something's changed, presumably a switch, go away and read all this and process it and then dump it back out on the lights for me, please. But if it hasn't, don't. So if you've got a lot of inputs, like say there's a few of these things, you might want to read them individually, you might want to read them all. You could have some quite heavy processing in here that you don't want to do every single time the code loop goes through, because you're doing other things. It's good practice, if you can, to only do it this way. If you're using, like I say, the 74165, you don't have a choice. It won't tell you something's changed. The only way you'll know is to do it. But let's clear that bit at the bottom, because we're not writing out now, and let's do this. And this is why I've switched that writing out function off. Something has changed, and we're going to run through and we're going to write something out and what have you. It gets the value it reads back incorrectly because it doesn't go and read it again. So yeah, but now do this and it's pretty much instant, and it works. And it's fairly straightforward. There are other functions, so you can read a single pin. To be honest, this is the way to do it, is use this bit shift. The only time you'd really want to read one pin, say you had 1 input and 7 outputs, or you don't like doing this bit shift operation, to like, well, I've read this, I've now got to mask it to find individual bits. You can say, yeah, just read a single pin, and the library's got a function to do that. But it works, and it works quite nicely. So we now come on to it. So we've sort of seen, well, what is it? We've seen what it does. We've seen how to use it. Okay, why? I mean, why? What is the point in using one of these things? And sometimes you actually find the answer to that one gets a little bit convoluted. For example, Leopard Street, I have got the DTC8 block detection boards. They're active low, so they're perfect to use with one of these things. And I've got relays, which are also active low because of the way the relays are configured on their little boards. So one of these things can control relays and it can read inputs. And I use the one that's got 16 pins, and some of my board controllers have got 2 of them, so I've got 32 pins available to me. Typically I've got about 16, 17 inputs, usually 16. It'll be 8 on one chip and 8 on the other. I use the low bits as inputs, I use the high bits as outputs. Just the way I've written the code. You don't have to do that, you can do anything you like with it. I went with that because it gave me a way to do it quite easily in standard code. But what it means is I've got those 32 pins for input and output running off 3 pins on the ESP32. I've got the 2 data lines, which I'm using anyway because I've got a Servo controller which uses I to C. So it's using these 2 wires. So I've already got these 2 wires connected. The only extra wire I'm adding is the orange one, which is for the interrupt. So for the cost of 1 wire, effectively, I've added 32 inputs, or 32 inputs or outputs to my my board. Now I'm not taking advantage. You can run these wires. You don't want them too long. No more than a meter. I would probably not go much more than about 50 centimeters. But what it can mean is you can have all the lights and everything on a control panel controlled by a circuit board stuck to the back of the control panel, and then just these 2 wires come out, or 3 wires come out, plug into your microcontroller, which might be at the bottom of the box, connected to a whole load of other bits and pieces. Very straightforward. And if you're only using it for output, you don't need the interrupt wire. Although, to be honest, if you're only using it for output, there might be better options. This is useful where you need the input and the output. But you can have a little modular control panel. As you see here, I've got 4 switches and 4 of these. Well, what if these switches were push buttons? Maybe 2 push buttons, and then another 2 on the other side. This could be, say, for a point or a signal. Throw it, close it. Danger, caution. And then these outputs could be LEDs that sit next to them. Maybe the buttons light up. So you can see, I press this button here and that button now lights up. And it's gone away, it's gone into here, and this has gone, I'm going to do something else. But instead of it being a push button that lights up, it's a push button with a light in it. There is a difference. Some push buttons, you connect the power, and if you press them, they light. What I'm talking about here is you've got a button that's got an LED in it. So you can press it, say changing a point. The bottom one is illuminated and we want the top one. So you press that, and the first thing that happens is both lights go out. And then a short while later, when the controller says, yeah, that point's finished moving, this one comes back on. So you've now got an indication. Same with the signal. You might not want it to change immediately, or you might want it to change to danger immediately, but then take a little while to clear. You can do, there's lots of little bits and pieces like that. Now, so yes, I use this for the block detection. The PCF8575, as I've mentioned, is a little bit bigger than this. They come on breadboards. They're fairly cheap. You can get this little board here on. You can get these chips for AliExpress on a header for about £4. Oh, sorry, that's on eBay for about £4 on a breakout board. So you don't need breadboard to use it. You just use the little DuPont wires, plug it in, and away you go. These little chips, £3 for 10 on AliExpress. So if you don't mind doing a bit of wiring, and these things will fit onto stripboard perfectly. Put them in sockets, although the socket can actually cost more than the chip, but it does help. You can drive displays with them. You can also use these for, as I've said, this can sync up to 20 milliamps per pin. It says a maximum of 80 for the chip. So if you can drive all LEDs, use like a 1K resistor, so they're on 3 milliamps or something like that. Then if all 8 of them are on at once, it's within the spec of the chip. You might run out of current sync capability on a microcontroller. But if you use a bunch of these things can have their own power supplies, which is another little bit there. But basically, yeah, it's an input-output port expander. If you think of that, that's giving you 8 more pins. You use a couple of pins over here which can drive these. As I say, you can drive 8 of these. There is actually a PCF8574. Sorry, a PCF8574A, and the only difference is it uses a different address range. Identical software, so you can actually have 16 of these things. 8 of the normal ones and 8 of the A variant. So you can get an awful lot of pins on this. If you are just trying to drive LEDs as outputs, there are better ways of doing it. I'll just say that one now. There are better ways. But if you need a mix of inputs and outputs, and like I say, I decided on my board controllers for most of the boards at Leopard Street, I don't need more than 8 inputs, because there's only 2 boards that have got more than 8 electrical blocks on. And at the moment, there's no board with more than 6 points. So one of these chips could read all of the inputs and drive all of the outputs it needs to for the frog relays. So it's quite simple to do. Do that, a little bit of code, away you go. So, anyway, that's enough. I'm going to play with the LEDs because I like playing with LEDs. I like LEDs to be on. Do that. In this video, we've had a little look at this PCF8574. We've seen what it does, how to make it do it. We have referenced this datasheet, so let's have a little bit more of a look on it. So it says down here, I2C bus to parallel port expander. And what it means by that is you get the 8 bits together. So you can send this data over the serial bus and put out 8 bits. There are uses for this, even if, I mean, the 595 chip is quite commonly used to drive LEDs. It's not on an I2C bus. So if you're already using the I2C bus, these are good. If you want to use something else, you'll be using more pins to do it. So these are good. 100 kilohertz. That can be a little bit of a drawback. There are some of the other chips can run into the megahertz range, much faster for data. Does it matter? Probably not. Not for a railway. Operating supply voltage 2.5 volts to 6. Non-over voltage tolerant I/O. That matters. I couldn't put 5 volt inputs on this thing. But if you notice, I'm not putting a positive voltage input onto it. I'm connecting it to ground. So actually, I can have this torque to 5 volt sensors as long as those sensors are what they call sort of open collector, active low. So they don't put a voltage on these lines. What they do is connect them to 0 when they want to do something. So we've got that. 8 bits we've seen, latched outputs. You see this is total sync capability of 80 milliamps. Active low, open drain, interrupt output, which is the orange wire. 8 programmable addresses, so we've got that. Low standby current, that's an interesting one. 2.5 microamps. So if this chip isn't syncing or anything, the power it draws is remarkably low, which is quite good. They give you a whole list of things that you can use it for, which remarkably, when you look at it, tends to be exactly the same on just about every single datasheet you see. We've got, and somewhere, I'm just trying to find this specifications section here, which is in here somewhere. I think it's near the back. Yeah, where are we? Contact information, trademarks. You get a lot of information in these. For example, there's all the timing diagrams for, which is timing diagrams. You don't have to use the library to control these. You can actually say to it, I want to do this myself. Use the library, it's easier. So here we have the characteristics. This is the bit that's useful to be able to learn how to read. So supply voltage, minimum 2.5, gives you a maximum. Supply current, this is what it'll drag on. Standby current is obviously a lot lower. Power on reset voltage is what you need to give it to tell it to reset. So you don't actually have to turn the power off to make it reset, but if it goes below 1.3 volts, it probably will. Tells you what your input voltages are. So assume for a minute the input was 10 volts. It's not, but it makes the maths easy. Anything, in that case, up to 3 volts, so it's anything 0.3 of your supply voltage or lower will be seen as low. Anything 0.7 of your supply voltage or higher will be seen as high. There's a big gap in the middle of there. This is what I meant about floating pins. Big gap. Don't go there. Give it a voltage it wants or give it less. But what it does mean is you can say if one of these has been driven on 5 volts, it might react to a 3 volt sensor. Yeah, you see on that. We've got the current capabilities are further down here, so we've got the 300 microamps, and the 25 is what its output current is interesting because low level output current, it's not actually an output, it's an input at that point because it sinks the voltage in. And then you've got some other bits and pieces down here towards the bottom about what you need to do with the address inputs to make that work. It's quite simple. This one notes that it will only run at 100 kilohertz. There are some of these that will go at 400. There are some of them that will go to megahertz as well, which I don't have. But there we go. So, I was going to look at exactly how I'm using these chips in a bit more detail. I think that's probably for another episode. This was aimed at being a bit more generic. How can you use one of these things? And the way to do it is literally, this bus you don't want to be particularly long. Other buses can be longer, but one of these under your station, maybe at one end, or maybe in the middle, and you've got like wires going out either side on this bus, talking to a few of these, controlling points, maybe controlling lights. Sorry, just to smack the camera again. So there we go. We'll look at the other way, which is basically the shift registers in another video. And they've also got a trick. One thing you can't do with these LEDs is tell them to dim very easily. You could use, like I said, a PNP transistor and have a pulse width modulated source which goes into here to dim them. A little bit awkward. There is another trick. Not on this, on the 595 shift register. We'll have a look at that when we get onto it. Anyway, I hope you found this useful, or at least slightly interesting and not too dry. I'm aware these electronics videos don't do as well as the I'm running trains videos. I don't care. This I think is actually useful information. Possibly. Or at least useful enough information to think, I might be interested in that. I'm going to go and Google someone who knows what he's talking about. Google a guy called Ben Eater on YouTube. He really goes in. I mean, this is a guy who's built his own microprocessor on breadboard with LEDs to show you what it's doing and how it works. And it's a lot more interesting than it sounds. But anyway, that's it for this episode. Thank you very much for watching. As usual, likes, comments, shares, whatever, welcome. I have had a few comments picking up some errors in previous videos. There's one of them wonderfully where I'm pressing a button to change a light. It flickers and it flicks straight back again. There's an error in the code. So I will do a bit of a catch-up at some point. But until then, enjoy what's left of your week and enjoy your weekend. I will see you again probably Saturday evening with another railway video. And we'll be back next week with more electronic stuff. So until then, goodbye. Meanwhile, I'm going to play with these lights. Blinking lights, blinking lights. Okay, I'll stop it now. Thank you for watching.